Okay, guys, we're still in chapter 6, but now the second half of chapter 6, we're going to switch gears a little bit and talk about electricity and the force of charged particles, the force that exists between charged particles. So please be following along in your chapter 6 guided notes. I've got some pictures I think we're going to learn about. So why lightning occurs, okay? We're going to study why is there this charge that exists between clouds and the ground and this discharge of electricity known as lightning. Okay, we'll study a little bit of electricity like, the electricity that comes from the outlets of your house and goes to appliances or to light bulbs, so how it all works. We'll study that a little bit. So it's kind of interesting, and I hope that you will like it, but please be following along in your guided notes. Here we go. We need to review the structure of the atom. It's been at least a year since you guys have had chemistry, so let's look at it. The atom is made up of 3 particles. What 3 particles are they? Good. The proton, the neutron, and the electrons. Those are the 3 particles that make up an atom. Let's talk about their electric charge now. A neutron. It's neutral. That's why it's called a neutron. They have no electric charge, so their charge is 0. A proton, though. What charge does a proton have, guys? Positive. Proton has a positive electric charge, so it has a +1 charge. Okay, electrons then are what? Negative. Yeah, the electrons are negative, so they would have a -1 charge. And most atoms have the same number of electrons as protons. If you look at carbon on the periodic table up here, carbon has how many protons?
11.
It has 6 protons. How many electrons would it have then?
Oh.
How many electrons would a carbon atom have? 6. Yeah, and the 6 protons are positive, so you've got a 6 plus, and the 6 electrons are negative, so you got a 6 minus. So what do you get if you take a positive 6 and subtract 6?
A 0.
0. So it's electrically neutral, right?
Yeah.
So they're electrically neutral. Does it have to be that way, though? Can carbon lose or gain electrons?
Yes.
Yeah, and when it does, it's called an ion, a cation, or an anion, and then it would have an electric charge. So.
Oh, I don't have my phone.
Okay, let's go over some rules for charges, guys. This is going to be very important throughout this chapter. Like charges. Do like charges repel or attract each other? Like charges repel each other. For example, if I had an electron here and an electron here, let's say I brought them close together and I let go. What's going to happen? They're going to repel each other. They're going to move in opposite directions. So like charges repel. Same thing with the proton, right? If I had 2 protons and I brought them close together, let's say we tried to hold them here, and I let go, well, they're going to repel each other. They move in opposite directions. Like charges repel. But what happens with opposite charges? Opposite charges attract each other. Okay, they attract each other. So if I have an electron here and a proton here, and I brought them close together and I let go, what's going to happen? Well, they're going to stay together. They attract each other. So opposites attract. That's where that saying comes from. Opposites attract. All right, practice problem number 8. Let's see if you guys got this. It has 3 parts. Part A. If 2 protons, so they're protons here. First of all, what charge does a proton have? Let's remember. Positive. Okay. So if you had 2 protons, and you brought them close together, and then you release them, what's going to happen? They're going to repel each other. Repel each other. Yeah, they're going to move apart. Okay, like charges repel. Part B. Now what if you had two electrons? What charge does an electron have? Negative. So if I had two negatively charged particles and I brought them close together and let go, what's going to happen? Yeah, same thing. They're going to repel. They're going to repel each other. Okay. Part C. If a proton, which is positive, and an electron, which is negative, are brought close together, what will they do? They're going to attract. So hopefully in your guided notes you've kind of filled that out. These guys will attract each other. Okay, here's what this video is going to be about. The main part of today's lesson is Coulomb's Law. Okay, Coulomb's Law. So let's get into it. There's this guy, Charles Augustin de Coulomb. He was a French physicist who found the force that exists between two charged particles. So if I have a proton and I have an electron, yeah, they're going to attract each other because there's a net force. There must be a force that's causing them to move toward each other. Well, he found the magnitude of that force, and he come up with an equation to help us calculate it. Okay? It's called Coulomb's Law. Yeah, he published his work in 1785, so yeah, he lived in the 1700s, and that's why he kind of looks like, George Washington, sort of. Kind of that same style, though, right?
Yeah.
Okay, and so he published his work in 1785.
Yeah.
Here is what he found. Okay, in order to calculate the force that exists between a proton and an electron, he came up with this equation. Okay, let's talk about it. In your notes, you're supposed to fill this out. F sub E is for force electric, or the electric force. The electric force, the force that exists between charged particles. It's called Coulomb's Law. Well, the electric force is equal to K. K is a constant. Coulomb's constant. It's equal to 9 times 10 to the 9th meters squared Newton divided by Coulomb squared. So K, I will always give you, but it's easy to remember, 9E9. Again, the units. Your distance has to be in meters, your force is going to be measured in newtons, and your charge, that we'll talk about in a second, has got to be reported in coulombs. Okay, so K is our constant. We're going to times that by Q1. Q1 is the charge of the first particle. So whatever the charge is, and it's going to be reported in coulombs. Q2 is the charge of the second particle. Again, it's reported in coulombs. And then we're going to divide all of that by the distance between them squared. So D is the distance between them, but don't forget to square it. Okay? All right, so let me point at one. You tell me what it means. What is F sub E? Yeah, the electric force. What's K? The constant. What does it equal? 9 times 10 to the 9th. What's Q? It's the charge of the first object. Q2. Charge of the second object. What do we report Q in? What's the units? Coulombs. Yeah, in honor of Coulomb. Okay, and then D, what's D? The distance between those particles. And what do we got to do to D? Square it. So this inverse square law still applies, right? It still applies. In fact, you're going to notice a lot of similarities between this equation and what other one?
The one we just did.
Yeah, Newton's universal law of gravity. Okay. All right, so the electric force, let's look at it for a second. There's two types of forces we've talked about in physics up to this point. There's contact, which means you have to be touching, but there's also forces that act over long range where you don't have to touch. Do particles have to touch in order for there to be a force? No. So what kind of force do you think it is? It's a force, it's a long-range force. Yeah, it's force at a distance. Okay, the magnitude of the electric force depends on the distance between the two charged objects. We just saw that with the equation. And Charles Coulomb performed electrical experiments in the 18th century. That's why we will call it Coulombs Law. Every time you see that equation, I'm just going to call it Coulombs Law. All right, so let's look at Coulomb's Law, or the electric force, and compare that to what we just got done learning about, the gravitational force. Aren't the equations very similar? So in your notes, you're supposed to write these down. The electric force is equal to K times Q1 times Q2 divided by D squared. Well, if you contrast that to Newton's universal law of gravity, the force of gravity is equal to big G, which is the gravitational constant times the mass of the first object, the mass of the second, over the distance between them squared. They're very similar equations, aren't they, guys? But there are some differences. The K is a constant, but it's not going to be equal to the same magnitude as G. Q is different. It's a charge of the first object. Q2 is the charge of the second object. But they're both exactly the same with distance squared on the bottom. So we should be familiar with using the equation. So let's try using it. Okay? Practice problem number 9. We're going to use Coulomb's law to solve this problem. So the first thing that we're going to do is write down Coulomb's law. F sub E is equal to K times Q1 times Q2 all over D squared. Now let's read it and then plug in to our variables here. Object A has a charge of plus 3.2 times 10 to the minus 11th coulombs, while object B has a charge of minus 5.6 times 10 to the minus 12 coulombs. They are 2.6 meters apart. Do they attract or repel? And how much electric force is present? Okay, so let's go and plug in. Again, K, I will always give you 9 times 10 to the 9th. So let's plug that in here. So 9 E9. What's Q1, guys? Good. Whoops. So 3.2 e to the minus 11. Okay, what's Q2? It's a negative 5.6 e to the minus 12. Okay. And then we're going to divide that by d squared. So divide by, what's the distance between them? Yeah, 2.6 meters apart. So 2.6 goes here. But guys, don't forget to square that. If you're having troubles getting the answer, that's probably what you're forgetting to do. So watch that. Okay, I want you to put this in your calculator, and I'm going to come around and see the answer. Okay? So if you're watching the video, please put that in your calculator right now and see if you can get what the magnitude of that electric force is. Okay, so let's see how you did. You should have got this as your magnitude of the force is a minus 2.39 times 10 to the minus 13th. And guys, what is the units for force? It's a Newton, okay? So a couple things we need to talk about. First of all, is this a very large force or is it kind of small? It's really small, right? Times 10 to the minus 13th newtons, we'd have to slide this decimal 13 times to the left. So it would be 0.00. You know, it's very small. So between charged particles, there's not a very large force, right? Very small. Another thing we should talk about. Can you have a negative force? No, not necessarily. You can't have a negative force. What is the negative sign telling us here? Okay? Well, if you look at what was happening, there was a positively charged particle here. There's a negatively charged particle here. When you have a positive and a negative, you're going to get a negative out, right? So a negative sign on the Coulomb's law tells you that it's going to be what kind of force? Attracting or repelling? It's an attractive force. So the negative sign just really tells you that they are being attracted to each other. Does that make sense? So what if you get a positive number out for the force? Then it's repelling. Then we would know they are being repelled. Okay? Because look, if you have a proton and a proton which is positive, would they repel each other? Yeah, and your force would be positive. What about an electron and an electron? What's minus times a minus? Still positive, so they're still repelling. So again, a negative sign tells you it's attractive force. All right, let's try another one. I want you guys to try this one on your own. If you're watching the video, please try it on your own. I told you I'd always give you K. K is equal to 9E9. Okay, so please try it. Hit pause on your video and try it first. Okay, so let's see how you did with this one. Coulomb's Law, let's write it down. The electric force is equal to K, that electric constant, times Q1 times Q2, all over the distance between them squared. So now let's plug in what they gave us. So K is going to be 9 times 10 to the 9th. Q1, it told us right here, was 4.5 times 10 to the minus 7th Coulomb, so we don't have to worry about the units there. Q2 was 7.2 times 10 to the minus 8th Coulombs. And the distance between them was 1.5 meters. Don't forget to take the square of that. Okay, so when you put that in your calculator, you should get that the electric force is 0.00012996. Usually we will put these in scientific notation, so if we switch that to scientific notation, that would be equal to 1.296 times 10 to the minus 4. And what's my units, guys? Newtons. Okay, a couple of questions that I have for you. Is it a large force or a small? Small. It's still small. It's times 10 to the minus 4th newtons. That's very small. Which is expected between particles, okay? Is this an attractive force or a repelling force? It's repelling. How do you know that? Because this was a positive value, right? And if you looked here, we had two positively charged particles. So if we put a positively charged particle near another positively charged particle, these guys are going to be repelled. So a positive sign for Coulomb's law tells you it's a repulsive force. Okay, so we did get it right. They just rounded theirs. Okay, so final slide on this video is right here. So the sign of the electric force, we've talked about this before, but if you run the numbers through Coulomb's law here and it comes out to be negative, what kind of force is that? So if it's negative, that's an attractive force. We've got to remember that. If the electric force is positive, that will be a repulsive force. All right. Guys, I want to give you some more practice with using Coulomb's law. So I've got a worksheet. It's titled Coulomb's Law Worksheet. Please go to your student workbook now. Again, it's called Coulomb's Law Worksheet, and hopefully this helped.